Hello, everybody. Happy New Year and welcome to 2021. Today is the sixth installment of the Bridge Preservation webinar series hosted by the Concrete Preservation Alliance. So let's get this show on the road. My name is Scott McCullough with Vector Corrosion Technologies. And as always, I'll be serving as your faithful moderator for the next hour or so. Now, I said this before, but today I'm bringing the receipts. I just checked the list for the past 6 webinars, all the registrants, you folk out there. And today we just passed 4,000 registrants for the first 6 webinars of this series. And those registrants have come from 42 different countries all around the world, which I personally find remarkable. It's very global. So just as a quick explainer to anybody who hasn't joined us in the past, the Concrete Preservation Alliance that hosts Webinar Wednesday is a network of committed members committed to advancing the education of concrete preservation and sustainable infrastructure renewal. We draw on the expertise of our member organizations to host these webinars, like we have our speaker today, Dave Whitmore. And our aim is to share best practices and innovative approaches to saving structures. Here's the list of our current members, and we are growing all the time. As I mentioned last webinar, we added 3 members just last month. Before I introduce our featured speaker for today, I'd like to remind everyone that we record each and every webinar Wednesday and post the recordings along with the speaker's slide deck here at the homepage of the Concrete Preservation Alliance, wesavestructures.info under the events tab here. Everything is absolutely free of charge as well. You'll also find a list of upcoming webinars that you can register for. And as I mentioned, we're only halfway through the series, so I do hope you'll join us for the remaining webinars. We should put together a fancy t-shirt or something that can signify that you've attended all 12 webinars this year. So I'll get working on that as soon as I can. So on to our featured speaker of today, a man who needs no introduction, as he's been a leader in our industry for literally decades. Dave Whitmore is the President and Chief Innovation Officer for Vector Corrosion Technologies, and consequently my ultimate boss. So feel free to flood that comment section with praise for my moderating skills. That'd be really much appreciated. Dave is a registered professional engineer, a NACE certified cathodic protection specialist, and he serves on a number of repair, corrosion, sustainability, and education committees of ACI, ICRI, and NACE. He is a fellow of the American Concrete Institute and the Canadian Society of Civil Engineers. He has been involved with the U.S. Federal Highway Administration on the Strategic Highway Research Program, SHARP, as well as SHARP 2 projects with regard to electrochemical chloride extraction, cathodic protection of concrete bridge structures, and bridges for service life beyond 100 years. Now, when Dave is not bouncing between Indonesia, New Zealand, and the Middle East, he lives in Winnipeg, Manitoba, in Canada, with his wife, Wendy, his 3 daughters, and his 3 grandkids. In his very limited spare time, Dave loves to get on the water in his trusty canoe and enjoy the great outdoors. So, as I mentioned, Dave is quite a globetrotter, and true to form, we've caught him today in Newfoundland, Canada, one of our great Atlantic provinces, where he's working on an important project. So Dave is going to share with us his experience in the area of evaluation and protection of bonded post-tension tendons, including the evaluation of grout condition and identifying voids and soft grout using non-destructive methods, as well as the history and development of a rather elegant corrosion protection solution called post-tension impregnation. So Dave, before we get going here, we have a photo of you looking very intently at a clipboard. What's going on there?
Thank you, Scott. That's a photo from a number of years ago when we were on an impregnation project, and I am simply measuring the amount of material that was impregnated into a post-tension tendon before moving on to do the next one. So nothing super special there, but you probably found that photo in the project archives, I assume. Anyway, thanks for the introduction, Scott. Thank you everyone for attending the seminar this afternoon. In the 45 or 50 minutes that we have available to us, my objective is to talk about the evaluation and corrosion protection of bonded post-tension tendons. And I thought I'd start by just showing you a picture of a highway interchange. This happens to be in Tampa, Florida. It's the I-4 connector interchange. And in this photograph, you see 8 or 9 post-tensioned bridges, all as part of the same junction. And post-tension bridges are a very major and important part of our infrastructure and of the bridge network that we have around us. Post-tensioning started a number of years ago. A man named Eugene Freycinet first proposed the use of post-tensioning in 1928. He did a number of experiments and worked on building elements and some beams. But by 1941, the first post-tension bridge was built, and it was built in France. After the Second World War, there was an increase in popularity of post-tensioning, and part of that was driven by the steel shortage that existed, and post-tension structures you more efficiently use the steel that's in them, and so that, in that reason, that was one thing that helped drive its use. The first post-tension bridge in the United States was built between 1949 and 1951. It's in Philadelphia, in the Philadelphia area. The bridge has been rehabilitated, but it still exists today. And I'd say overall these structures have been very durable, and they have served their purpose very, very well. Post-tension bridges are structurally efficient, and post-tensioning has made long-span bridges more practical and, I would say, generally more economical than they were before. One specific type of post-tension bridge that is quite common, and you'll see in a few of the case studies, are segmental, precast segmental bridges. The first one of these built in the United States was built in Texas by Texas DOT in 1973 in Corpus Christi, as you can see here. And that bridge is still in service as well. I had the privilege of being able to inspect that bridge along with the then chief bridge engineer for Texas DOT, and generally this is in really good condition. Has one kind of issue, a detail that they probably didn't know about at the time when they built the bridge. The end anchorages for the post-tensioning actually come up and end in the deck slab, and so the anchorages are somewhat sensitive to getting contaminated with water or having water infiltration because the anchor pockets actually end in the deck. Other than that one issue, the structures served its service very well and has been in good condition. Now, if we talk about the durability of post-tension, grouted post-tension structures, corrosion and durability really come down to the quality and uniformity of the grouting. If you have a situation where the tendons are well grouted without any voids and the quality of the grout is what it should be, you very rarely will see any corrosion issues. The photograph that you see in this slide, and I'll just get a pointer here, an opening has been made in the side of the concrete to expose the duct. You can see the duct has been opened, metal duct here, and inside the metal duct the grout has been removed to expose a couple of strands in this tendon. And you can see that the strands are in good condition. They've been embedded in good quality grout, and there's no sign of any corrosion activity. This is what ideally we would like to see everywhere. Unfortunately, in some cases, there are defects in either the grouting itself, the material, maybe the installation of the grout by the contractor, or possibly the design details that allow for the presence of voids or water to get into the tendons. But this can lead to corrosion, and the slide that you're looking at right now is a collage that was put together by a friend of mine, Ivan Lassa, who was, he's now retired, but was working for Florida DOT at the time. And this collage shows some of the main causes of corrosion, or the result of corrosion in different situations for post-tension tendons in bridges. The tendon here up in the upper left-hand corner, as well as the one on the upper right-hand corner, these are both examples of where you have voids in the grout. And obviously when there's no grout there, you don't have the protection that you expect on the tendons, and they're vulnerable for corrosion. That's one issue, and we'll talk about that later. The two pictures in the center are situations where you have segregation of the grout. In the bottom case, you can see segregation and the tendon is not fully full of grout. Sometimes water may float to the top and then you have a void left over later on. In other cases, the tendon may be fully full of grout, but because of segregation, you have good quality grout at the bottom and maybe not so good at the top, and you get corrosion. In the bottom left corner is a situation where the tendons were grouted on this bridge. The DOT realized that there were voids because of bleed water voids, and they came back and re-grouted the voids a number of years later, thinking that that was dealing with the issue. And unfortunately, corrosion continued at the interface between the old and the new grout, and you can see that the strand has been, or the tendon here has basically been essentially severed at the location where the two different grouts meet. We can talk about that later if you're interested. And in the bottom right-hand corner, we have an example of a structure that is exposed to chlorides in the environment. This one happens to be a Pennsylvania DOT bridge, and chlorides have soaked through the concrete, gotten down to the metal duct. They've corroded the metal duct entirely, and you can see that the strands inside of the duct are now corroding, and it's led to some concrete damage that is clearly visible. So there are many reasons why you can end up with issues that result in corrosion, but I'm going to just touch on the two most common ones. The most common, in my experience, is the presence of voids. So if you have a void in your grout, then you have a location where the steel may not be protected. You have a location where water can collect, and even worse, salt water can collect, and you can have severe damage and corrosion in the areas where you have voids. One of the common things that lead to voids is what is referred to as bleed. So if you have a standard cement water grout, in order to make it pumpable, you actually have more water in the mix than what is required to cure the cement. The result of that is that after the cement grout is pumped, some of the excess water will essentially float or bleed to the top, and this will end up leaving a void after it either evaporates or is absorbed into the remainder of the grout. The photographs that you see here are from an American Segmental Bridge Institute training session. The column on the left here was grouted with the cement water grout, and the photo on the right is the same column taking the photos taken 24 hours later, and you can see that there is a height here at the top that the grout level has settled. This is generally referred to as bleed. So this is the original elevation of the grout, and the grout is settled down to here. And with cement water grout, typically you're going to have somewhere between 3 and 5% bleed, depending on the amount of excess water. and that is going to mean that you're going to end up with 3 to 5% voids when the grout is fully cured. And that's assuming that everything is properly done by the contractor and there are no voids because of air pockets, or the tendon was essentially fully full before settings started up. So this is one issue that can lead to problems, voids. And another issue that definitely can lead to problems is if you have segregation, or sometimes it's referred to, in extreme cases, could lead to soft grout. In this case, a lot of agencies have moved from using cement water grout to using prepackaged grouts. These grouts have additives to prevent bleed or to greatly limit it, and that's good. But if you add too much water to those mixes, or in some cases, maybe if the bags are a little bit old, you can have segregation occurring. And that's simply a separation of the material based on density. And you'll have at the bottom of the duct denser material, and the lighter material will float to the top. You may not have any voids at all, but you'll have differences in material properties that can lead to corrosion between generally the strands in the good quality grout at the bottom will be protected, and the strands in the lower quality grout that floats will typically corrode. And one of the things that drives that corrosion is that where you have the higher water content grout, you tend to have a concentration of water soluble salts like chlorides and sulfates, and you'll end up having a corrosion cell, a concentration cell, where you have the higher sulfate and chloride content strands, they will corrode relative to where you have lower. And that's something that you should be aware of. In extreme cases, this soft material on the top may be so soft that it actually doesn't harden, and it's really more like wet clay, or if it dries out, as you see here on the picture on the bottom, on the right, upper and lower right, it's more like chalky, just very powdery material. So those are the two main things that typically lead to corrosion problems: voids and segregation or defective grout. And in the next portion of the presentation here, I'd like to move and talk a little bit about techniques that can be used to identify areas where you have issues. So the first technique that I want to talk to you about is the use of ultrasonic evaluation. This is a very effective technique in locating voids and the presence of either water or soft grout within the tendon assembly. The equipment that you see here is equipment that actually we make, but there are other kinds of things around that you may be able to use as well. And this equipment basically is doing impact echo and pulse velocity concurrently. And if you move along a tendon assembly, you can pick up where you have voids or defects in the grout. The video here will probably show this a little bit better. So here are a couple of people in a man lift, and they are going along and taking measurements and running along the line of the tendon. The person on the left is using an impact device that has a precision impact on the concrete, and the sensors on the right are collecting the impulse response from that impact along the line. And if you move along the tendon in this way, you can pick up very easily where you've got problems and where it does not appear like you have any problems. Just an example of that, this is a picture of a bridge. It's a small bridge. It's a pedestrian bridge over a section of expressway out on the west coast. And the DOT was concerned. They had reviewed the construction records, and they thought that maybe they had some problems with the grouting on that post-tension pedestrian bridge. The people in the basket here are doing the same testing that you just saw in the video. and they identified a couple of areas where there were some big anomalies. Those areas were opened up, and you can see here that in this section there was no grout at all. And that was identified using the sonic ultrasonic testing technique and equipment. So if you identify an anomaly with this equipment, one option is that you can chip the concrete, make an opening, remove the duct, and take a look inside. And in some cases, that's the appropriate route. In other cases, you might not want to make that big of an opening in the concrete, so you may want to use a borescope. And in this slide, you can see on the left-hand photo, one of my colleagues, Brian Pales, he's on the top of an LNG tank that is post-tensioned. It has both horizontal post-tensioning and vertical post-tensioning in the shell. And he has a borescope in his hand, and the probe from the borescope here is being inserted into a small drilled hole that is going in where the old grout vent tubes were. And from that drilled hole, you can take a look inside, and you can basically see inside where a void was identified, and you can see the condition of the strand. You can see that there was cement paste on these strands, so they were grouted full height, and then you had bleed water and the grout level settled, and you can see some areas where you've got some corrosion going on. The advantage of this is that you don't need to make a big opening in the concrete, and typically this can be done in a 1/2 inch or maybe a 12 or 15 millimeter diameter hole. And similarly, you know, you can do this on other projects. This is a different project on a different bridge, and you can see different borescope images that were taken from different defects that were identified, holes drilled in, and then borescope is used to determine the condition of the strands, as well as to get an idea of how big the void is. And so this gives you a way to verify in the field the non-destructive testing results that you're getting from the sonic ultrasonic techniques. And so if that's something you want to do, then that's available and certainly possible. There are cases where you may want to know what is the condition of the strands themselves. It may be grouted. You may not have any presence of voids, or you may not be aware whether there are or not. There is a technique available using magnetic flux that can be used to determine if you've got broken PT tendons, or more likely broken individual strands or wires. And I'm just going to show you a slide or two from a project that we did on the Sunshine Skyway down in Florida. And the post-tension tendons in question here are transverse post-tensioning that's in the deck of the bridge. The left-hand photograph here shows the equipment that was used. Essentially, this is a large electromagnet. You've got one pole of the magnet here, and you have the other pole of the magnet over on the other side. And this large magnet creates a magnetic field between the two poles. And obviously down at the ground level creates a magnetic field between the two poles down here. When you run this over top of the concrete surface and you go over post-tensioning tendon that is going in the same direction as the magnetic field, then you will induce a magnetic field response onto the steel itself. And when you do that, you're going to magnetize the steel, and one end of the steel is going to be magnetized south, like the magnet shown here in the center, and one side of the steel is going to be magnetized north, as indicated here. And if there are no breaks, if everything is continuous in the steel, you'll end up with a magnetic field curve that starts either high or low at one end. So high here like south, and comes down, and it would be a smooth kind of S-curve all the way down to the bottom right. If the tendon is completely severed, then you'll end up having two curves. You'll have south going all the way down to north, and then you'll start with a new south up here, and you'll come down all the way to south if it's completely broken, as illustrated in the little bar magnet in the middle here. More likely what you will see is that only a portion of the steel is broken, and that's going to give you a kind of result that you see here, where you have the majority of the steel going straight through, but where you've got the broken strands or the broken wires, it will tend to create a new north and south pole at the location where you have the defect. So this technique is not as widely used. There are limitations with it, like there are with anything else, but it is certainly something that you should be aware of, and in certain applications can give you really, really good information. Okay, so just want to move right now and talk a little bit about corrosion and techniques that can be used to determine the risk of corrosion activity inside grouted post-tension tendons. You saw the photo on the left at the beginning of the presentation, and it's clearly a photo of a situation where there's a void in the grout and there's exposed steel strands in that voided section. And these exposed steel strands are going to be exposed to potential for corrosion, and the behavior of those steel strands with regard to corrosion is going to behave something like what is shown on this graph on the right, in that the corrosion rate is going to be really low if there's little moisture there, and then it's going to increase, and then once it starts to go, it's going to go up very, very high. And for a standard temperature kind of condition, you'll get a single curve like this. If you have multiple temperature situations, then you're going to have multiple curves, but the idea of showing you this at this point is just to give you the idea. If the strands are in grout, the grout is going to create an alkaline environment around the steel. That alkaline environment is going to protect the steel from corrosion, and it doesn't matter whether it's wet or dry, the strands will be protected. If there's voids in the grouting for whatever reason, or if you're dealing with unbonded post-tension tendons that don't have any grout at all, then the corrosion rate of the voided sections, the tendons in the voided sections, or the corrosion rate of the unbonded tendons is going to behave like this, and is going to be very dependent on the moisture content that they are exposed to. If you know that, then you can take that information, and we use that relationship in a corrosion evaluation technique that we have. We call it PT corrosion evaluation. It's not a very innovative name, but it is a very useful technique. And with this technique, we typically make two openings into the duct. These can be small drilled holes, or they can be larger, depends on what you want. At one location, which we call here the import, we connect a supply of dry gas along with a flow meter, and we basically push the dry gas in at this location in the tendon. That pushes an air sample out of the out port. And again, with a flow meter, we run that through a sampling or a measuring unit, and we measure the moisture content of the air that is being pushed out of the tendon assembly. We can then take that information and we can plot it on a table like this. And this is a multi-temperature version of the table that I showed you before with the one simple curve. And based on the temperature and the relative humidity, you can determine whether you are in a high, low, or medium risk condition. So if you take a measurement down here and you're in this green zone, then your risk of corrosion is low. And honestly, you probably don't have any significant issues with regard to corrosion at all. If the moisture content is higher up here at the same temperature, then you're at a situation where corrosion is definitely possible, but the corrosion rate will be limited by the moisture content that's there. And if you measure something up in the upper red zone here, then you basically have a situation where the corrosion rate is not limited by the moisture content. It may still be limited by other factors like availability of oxygen, but you have more than enough moisture there for corrosion to go at a significant rate. This is what it looks like in the field to do this type of measuring. Here you have an external post-tension tendon in a post-tension bridge. Here you can see the outport. It's just a 1/4 inch diameter or 6 millimeter diameter tube that's been installed into the tendon, and that is connected to the measuring equipment. And so this technician is taking a measurement, and that reading is being recorded and logged in the equipment that you see here. The picture that you just saw was from this particular bridge, and it had a history. They had one tendon fail in this bridge, and we tested 4 other tendons, and we got basically 4 measurements that were all up here, and there may be other tendons that are not as wet or don't have as high a risk of corrosion as the 4 that we measured, but this is probably certainly one of the reasons why they had the corrosion issue that they did in the one tendon that failed. So there is a very strong correlation between moisture content and corrosion risk. And if you have wet tendons, then one option for reducing the corrosion rate is to dry them out. And so in the next few slides here, I just want to explain the process and show you a couple of pictures from a recent project. So in PT tendon drying, here we're using a supply of dry gas. We're pushing it into the structure at some location, and we're either pushing it in both directions as illustrated here, or often it's pushed in at one location and out at another. But either way, you're basically pumping in dry or desiccated air at a certain location, pushing it through the tendon assembly. It's evaporating moisture that's in the tendon assembly or picking up moisture that's in the tendon assembly, and the air that is venting out here is going out, and it's carrying moisture that's been picked up as it goes through the system. And you basically pump in dry or desiccated air, and you continue to do that until the moisture content of the air that you're pushing out goes below a certain level that you wish to have. And this has been done on a number of things. It's a very common technique for unbonded post-tension tendons as well, but in terms of bonded or grouted post-tension tendons, this is an example where it was done recently on a Florida DOT bridge, and the tendons are inside the girders of this bridge. If you're going to pump dry or desiccated air through the tendons, this is going to take a period of time, and you're not going to, from a cost-effective point of view, you're not going to do this with a bottle or a few bottles of compressed air or nitrogen. Generally, what you're going to set up on site is a dry air plant, and that is going to consist of a compressor, moisture separator, and then you're going to go through generally 2 types of dryers or desiccant dryers, and you're going to get the moisture content of the air or the dew point of the air down to usually around certainly -30 at a minimum, and probably around -40 dew point. Effectively, you're going to have air that's completely dry. That air is going to be piped out to the structure and then you're going to have that going, typically split into a number of different tubes, and then that's going to be injected into the tendons. This in here, you can see going into one tendon here, you can see a tube connected to a different tendon down here, and you're going to pump the dry air in at certain locations, and it's going to vent out at other locations. And at the vent locations, you can manually measure the moisture content, or as illustrated here, you can have an automated system, and you basically are monitoring the moisture content of the air that is being exhausted throughout the process. And as I said before, you continue the drying process until you get the exhaust air down to the level of dryness that you wish to achieve. And so if your problem is simply moisture, you can do drying. If you want to provide protection beyond that, you may want to consider something else or something in addition to that. And one of the things that sometimes is done in conjunction with drying or is done instead of drying is a process that's called impregnation. And this is a corrosion protection process for grouted post-tension tendons. And generally these are tendons which have either voids or some type of defective grout. It could be used to provide additional protection to tendons without those deficiencies, but generally this has been used on tendons that have been identified that have these deficiencies. The impregnation material is transported inside the strands, and it's transported and treats the full length of the tendon. And I'll explain in a couple of slides exactly how that's done. The impregnation material reduces corrosion by two mechanisms. The first is that in locations where you have voids and you have exposed steel, the material will form a coating or a film on the exposed steel surfaces. And so obviously that means steel in voids, exposed steel in voids, but it also includes the internal surfaces of the strands themselves, where corrosion can also be an issue. And the second mechanism is that the material soaks into the grout surrounding the tendon or the strand, and by doing so it improves the corrosion resistance of the grout. It increases the resistivity of the grout, and it also makes the grout more hygroscopic, or keeps water, and effectively keeps water away from the strands. Now, just schematically, if the end of the tendon is available, that's a very easy and convenient way to do this. As illustrated here, if the end of the tendon is available, you're going to basically make a connection to the end. You're going to pump the material from one end of the tendon, and it's going to travel actually inside the strands themselves through to the other end of the post-tensioning tendon. As it travels along, the material is also going to seep between the wires and into the surrounding grout. So just conceptually, that's what's happening if you have the ends of the tendons available. If the end of the tendon isn't available, then you're going to typically do this work from some intermediate location through a port, and the material will be introduced at that location. The material in these situations generally is going to go both ways from the intermediate port. Again, the principal transport mechanism is inside the strands themselves, and then from there it's soaking between the wires into the surrounding grout. In a typical tendon, you may have a number of strands. In this case, I think there's 19 strands, and those strands are grouted in, hopefully fully grouted into the duct, so that there's no real space or voids outside or the strands themselves. If we take a close-up view of the end of one of those strands, You'll see we have 6 outer wires. We have an inner king wire, and in between the wires here, we have what we refer to as interstitial spaces. And these are effectively longitudinal capillaries that run the full length of the tendon. And that's where the material is primarily traveling, is along the length of these capillaries. So just to give you a few examples, this is a bridge down in Florida. It's a beautiful segmental post-tension bridge. Has had a few tendons that were not properly grouted, and you can see here there are some external tendons and there are also some internal tendons in this structure. But the end of the tendons here are readily accessible. There are plastic end caps, and if you have this condition, a simple way to do this is to remove the plastic or metal end cap, expose the grout, remove the grout, expose the end of the anchorage and the end of the strands, put the cap back on, connect a hose to the grouting port, fill the cap with the impregnation material, pressurize it, and then go to the other end of the tendon where you've done the same removal and cleaning opportunity, and just wait until the material begins to appear there. And here you can see the material starting to seep out of one strand down here and another strand up here. Continue to wait, and the tendon on the left, I don't think material is coming out of these 2 strands at the time when the photo was taken, but you continue to wait until the material is visibly coming out of all of the strands at the other end. And it's very obvious visually when that's happening and when it's not. That project I just showed you was actually the first full-scale field project that we did for Florida DOT, and they hired an outside consultant to basically do some quality control inspection. They made some openings in the ducts that you see here, actually 24 of them in the first tendons that we did, and they removed the duct, they carefully removed the grout, and they wanted to verify that the impregnation material was in and around the strands, which you can see in this photograph. They continued the removal all the way around the perimeter, and they just visually verified that the material was present there. They put the duct sections back, regrouted it, and they've never done that again. Obviously, those tendons were pumped from one end to the other, but they just wanted to see what was happening at midpoint locations. In this picture here, this is a video from a demo that was done in the UK. A grouting contractor or a PT contractor there had built a mock-up, a tendon mock-up for a grouting verification, and then we used that mock-up for doing impregnation. You can see that the material, this is an opening that was somewhere along the length. The material was seeping out from between the wires, and at the end of the tendon, you can see that the material is coming out the end and dripping down and squirting out actually in a little bit here. This is only 10 or 12 meter long length, so it's only about 40 or 50 foot long tendon, and you can see the flow rate through that tendon is fairly high. In a full length tendon in a bridge where it might be 200 or 300 feet long, or possibly even more, it's still going to flow like this, but it's just going to be slower because of the longer length. So the previous 2 examples showed situations where the tendons were being impregnated from the end. This is one example I just wanted to show where intermediate ports were used. Here you can see the technician is drilling a port. So this is a 6 millimeter diameter or 1/4 inch diameter drilled hole. We're using special equipment so that it doesn't cause any damage to the strands. Here you can see the port is in, one of the ports is installed into the duct, and here you can see the pump assembly, and it's pumping material from a reservoir here down this hose to an intermediate location, and from that location is pushing the material in both directions. And when you're pumping from an intermediate location, typically you're going to pump until the material is visibly present at one or both ends. Here, and usually what you'll see is at the end of the duct where it goes into the diaphragm wall, you may see material starting to come out of small cracks in the concrete diaphragm wall. That's one sign that the material is there. And the other sign is that, you know, if you've got a concrete pour back on the other side of the diaphragm, you may have signs that it's leaking out around cracks between the pour back and the concrete segment itself. So in these cases, the work was done from an intermediate location because the cost and time involved in removing all of the concrete pour back to expose the anchorages was considered to be prohibitive. Here you can see just one little video from a mock-up, and so this is a tendon section with a 1/4 inch diameter or 6 millimeter drilled hole in from the side. The valve's opened and you can see the material is running out a strand that's running more or less in line with where it's being injected or impregnated, and it runs pretty easily lengthwise along a tendon once it gets, or along a strand once it gets inside. Here we're plugging the end of it with a very sophisticated plug to build up some back pressure. This would be typical of what happens when you have a longer length of tendon. And when you do that, you'll notice that instead of just running freely along the one strand that is clearly in, you'll notice that it starts to move across transversely across the section. So here you can see it's moved 15 or 20 degrees radially around the section. And from the end, you can see it's now coming out below where it was coming before. It's coming out this strand up here and up and to the right. It's now coming out another one down below. So basically it's moving across the section. The quality of the video here is not the greatest, but you get the idea. And now you can see it's coming out the bottom right-hand one, it's coming out the top right-hand one, and the last one for it to start coming is this one here. And this is there it goes, and it's coming diagonally opposite from where it's basically being pumped in. So you can see that the material can travel lengthwise inside the strands, but it also can travel laterally from strand to strand, and that's quite common to see. So that, I think, visually shows you that you can get material into the tendons. The next few slides here I just wanted to show you are to give you some idea of, you know, is there a benefit in doing this in terms of corrosion protection as opposed to just pumping something into the strand. So the slide you see here is very, very simple test. It's actually 2 pieces of strand, one of which was dipped into the impregnation material, the other one here was not, and then both strands were exposed to salt spray, and visually you can see there's a big difference in the amount of corrosion that's occurred. This test was basically set up to simulate a piece of strand in a void where it's exposed to the impregnation material during the impregnation process, and then the material just is absorbed or leaks away, and will there be enough of a film there to provide protection? So I think visually that is showing some benefit there. If you want more quantitative testing, you generally have to go with either galvanostatic or potentiostatic testing. In a laboratory setting, that generally means making standardized samples with a standard piece of strand, so everything is controlled, the position, the size of the strand, the length of it. That strand is connected to a potentiostat. The potentiostat is connected to a counter electrode as well as to a reference electrode in the cell, and you apply either a current if you are doing galvanostatic testing, or you apply a potential or a voltage if you're doing potentiostatic testing. And you can compare the corrosion resistance of different things very easily using these techniques. So just to not bore you with details, and if you want any more information on any of this, feel free to let me know or send me an email after the presentation here. But This slide is showing the results from potentiostatic testing of samples that were built with chloride contaminated grout. So 2% chloride contaminated grout, so quite a high chloride content. And you're applying a potential. So basically you're applying a voltage to these samples and you're measuring the amount of current that flows. And you're going to do that over a certain time frame, and a standard time frame for this test is 1 hour or 3,600 seconds. And during that time frame, you measure the current, and you'll notice for the untreated samples, the current is much higher, and after stabilizing, it actually increases with time. If you look at the treated samples with the same voltage applied to them, the current is much lower, and maybe it slightly increases with time, but it's definitely much lower and much more stable, which implies you have a great increase in corrosion resistance. You can summarize these charts by taking and essentially calculating the area under the curve, under each of those curves. And from that, you can basically get the total current or total charge passed. And you can compare the untreated samples to the treated samples, and you can see that there's a big reduction by doing the treatment on chloride contaminated samples in this case. Similarly, you can do the same type of testing, potentiostatic testing, but instead of samples with chlorides here, they're tendons with voids, 4.5% voids in this case, and you can see that there's a big reduction from untreated to treated samples in the amount of current or charge that's passed, which basically means you have a lot longer time frame to failure with the treated tendons. Finally, with regard to performance evaluation, I just wanted to show you the front cover of a report that Florida DOT issued. They did some testing, they made samples, and the photos here on the right are from the report. So they had samples, treated and untreated samples, treated and control samples as they call them, that were exposed to salt fog, hot salt fog conditions, and also exposed to saltwater ponding. And then after the end of the testing, they broke the samples apart. And so there are very interesting and good photos in there showing not only quantitatively, but qualitatively, you can see there's a big difference in the amount of corrosion between the treated samples and the untreated or the control samples in this evaluation that they did. So just to kind of wrap up, we've talked about a number of different things here, but I think just 3 main points to conclude. First is that post-tension tendons are susceptible to corrosion. Number 2, there are evaluation techniques out there that are available to determine the cause, the extent, and the location of problems. The 2 most common problems are generally the presence of voids in the grouting or the presence of defective grout. And number 3, there are corrosion mitigation techniques available to protect and extend the service life of grouted post-tension tendons in existing structures. So with that, Scott, I'd like to turn it back over to you, and if there are any questions, be happy to answer them if I can.
All right, so we'll start off with some from the beginning. I've been tracking them all here. Do you have to pre-locate the ducts before performing the ultrasonic test? Yes. Simple answer to a very important question. You need to do that to make sure that you're measuring a consistent situation all the way along, and then you measure along the length of the duct so that you're not changing multiple variables at the same time. Okay, perfect. We have a question from a fairly new bridge manager. What is the driving decision to look for voids or issues in the post-tensioning? He says, I can understand if the corrosion is visible, but what if it's not a visible issue? Yeah, that's a good question as well. I'd say in most cases, the corrosion is not visible unless you're
basically at or close to the point of failure. And I don't mean the structural collapse, but maybe a strand failure. I would say if you have a bridge that is grouted post-tensioning that was built in North America, if it was built before 2000, it was probably grouted with cement water grout, and you should expect that you have voids in the grouting if that's the case. The question is, how much void do you have? Probably 3% would be close to a minimum that you would expect, but it could be 5%, or it could even be more if the grouting wasn't done properly. So if you have something built during that time frame, then there's a very high probability that you're going to have voids, at least at the high points. And if you have something that's been more recent, and it depends where you are, even in the country and certainly overseas, there are some states in the US and there are some jurisdictions in Canada that are still using cement water grout, and certainly in other places they're not. If you have newer structures that are grouted with prepackaged grout, if it's done well, you hopefully don't have a problem with voids. You may just want to make sure you don't have a problem with segregation or soft grout, but the chance of that is definitely lower.
Gotcha. Okay, so if you do find a void, I'm going to paraphrase this one here. If you do find a void and say the client is insisting on simply filling the void with new grout, what would you suggest to them, or what are your comments on that?
Well, just be careful. You know, obviously, if you've got a void, you've got a physical, you've got a section which doesn't have grout. And so a lot of people just want to fill the void to make it consistent with other places that are not filled. I think you want to be careful that the grout that you're using to fill the void is compatible, similar to the grout that was used initially, so you don't create any potential differences between two different types of grout. But the other thing is, I think you want to be careful that there isn't a layer of chalky grout or soft grout or anything on the top of the section that you're leaving there. Usually when you have bleed water situation, the water floats to the surface, and so you end up with a void where the water lens was, and the good dense grout obviously stays at the bottom, but you're typically going to end up with a layer at the top of the grout, which is going to be a very high water content layer of grout. It could be very soft and chalky. It will be highly sensitive to carbonation. And in the situation where I showed where they had regrouted the tendons and then they still had corrosion failures afterwards, probably a big driving mechanism there was that they had good grout down below. You have a layer of chalky carbonated grout at the top of the original grout, and then you fill the top of it with new alkaline grout, and you end up with this nice little corrosion sandwich where you've got carbonated grout in between, and that's where all the corrosion is going to occur. You also end up adding water back into the assembly by the new grouting too, so you may reactivate or add water into that carbonated grout layer that may exist there.
Corrosion sandwich. I'm going to
long answer, but it probably depends on the specific project details, but that's one example where you can run into trouble.
Good stuff. Corrosion sandwich. I'm going to take that one away with me. And good one. So quick question specifically regarding the pedestrian bridge example you showed. What led the quality assurance team to investigate further? How did they know there was a grout issue?
Yeah, that's funny. I mean, that bridge was built, I can't remember, but like 10 or more years before the investigation was done. And they were reviewing the construction records and they realized, so the contractor was grouting the tendons from one end. They were pumping the tendons. They had a problem with their pump. For whatever reason, they had to stop grouting. They tried to regrout, but it was already set up. I think they couldn't, by the time they got it fixed, they couldn't figure that out. So they jump to the other end of the tendon and they pump grout from what was originally planned as the vent end of the tendon. They pumped it back towards where they had pumped. So the issue here was that they pumped back from the far end of the tendon, and they had a big air pocket in there that was not able to vent to anywhere. And so, you know, they grouted it from one end, they grouted it from the other end, but somewhere near in the middle section, you've got a big air pocket. Okay.
Next question is related to the ultrasonic testing. How does concrete cover affect the testing? Is there a depth which it won't work, or?
The cover over the tendon is not a big factor. It's probably more a factor of the total thickness of the concrete section itself. That's probably pretty, I mean, most cases you're dealing with section like the web of a box or something, and maybe a foot thick or 30, 40 centimeters thick. That should be perfectly fine. I was involved in one job where it was close to a meter, so 3 feet thick. It was very, very difficult to pick out the tendons in that very thick section. So I probably the limit is somewhere around half a meter, somewhere 50, 60 centimeters, or maybe 18 to 24 inches thick would be probably a limit, and it would be the section thickness. It would actually be the duct diameter relative to the section thickness that would be the driving factor there.
Okay. Just onto the PT corrosion evaluation, how long would it typically take to do an evaluation on, and the example was given, 150 meter tendon?
I mean, it will take you 150 meter tendon is pretty long, but certainly they are there. You may end up doing a tendon like that in sections. You may, depending on how it was built, because that's possibly, that may be multiple spans. It may be one long span, I suppose. You are probably, I mean, you can easily do that in a day. Let's put it that way. It'll take more time to get there and get set up, but the actual testing will take maybe a couple of hours, and it'll probably take you longer. Definitely will take you longer than that to locate the tendons and put in your ports and do those things. The testing itself, you know, probably do several tendons per day, but it'll be the work to put in the ports and get them set up that'll take the time.
Okay. We had a couple questions related to the gas. What's the composition of the dry gas? And maybe just clarify what it actually is.
Yeah, so for testing, very often we will use just a bottle of nitrogen for testing. It's readily available. You can take it to site. Just a bottle of compressed gas, like you would if you went and bought helium for your kid's birthday party, balloons. For drying, however, it's not economical to try and dry the structure by using bottles of nitrogen. So normally for drying, you're just using dried compressed air. Typically for drying, that's what you'd use.
Gotcha. Okay, we're getting close to the end here. We're a little over time, but maybe one or two more questions tops. Knowing how difficult it is to, I think they mean inject concrete, say for cracks, and the irregular result that gives, how far are you able to actually impregnate these cables? And I know it's not injecting into concrete per se, but what is the extent? How far can we go?
You can go a lot further than you think, than you may think anyway. Certainly 70, 80 meters, 250 feet is very, I would say, generally very easy to do. That's kind of a typical tendon length. I think the longest that we've done has been up around between 400 and 500 feet, almost 150 meters, but it starts to get quite slow if you're going to try and do that all in one shot. But I would say in most cases you probably are doing sections that may be 200 to 300 feet long, or maybe 70 to 100 meters long.
Okay, so that's effective in treating the entire tendon. Now, what if we have a case where the client is not interested in actually treating the entire tendon, but just say the localized areas where you found voids, for example? What would be a good solution there? Can you apply this same technique in just a localized manner, or?
Yeah. Normally, normally we, I'd say most often we do the entire length of the tendon, because once you're set up to do it, yes, it takes a little bit more time, but you're already set up and you're there. But yes, you can do the end. We did a job last year where we did basically the end of the section, so identified where the voids were. They were essentially at the high points, and we effectively just did the draped section of the tendons. So probably only let's say the last 10 meters or 30 feet of each of the tendons in those locations.
Awesome.
And there is some saving to do that, but it's not like necessarily like cutting it in half.
If there is a void or void settlement or bleed, even if the grout is properly placed, how can it be assured that the PT tendon will be protected? I assume the answer is it can't be assured.
Yeah, no, exactly. So if there is a problem, okay, so if you have a bleed problem, then let's assume the tendon was properly grouted at the beginning. It's completely full of grout, but then you have bleed. That bleed water is going to collect in the high points of the tendon. So if you've got draped tendons, it typically is going to be at the high points. Very often that's around anchorages. In vertical tendons, this is even more of a problem. And any steel that's in the bleed water section, or it ends up being in the void, is at risk. Now, depending on whether it was completely filled or for how long, you might have some grout residue on the strands. You can see that in some of the slides. That grout residue may provide a limited amount of protection, but nowhere near the protection of good quality grout. So you have a problem if you've got bleed or voids for any other reason, and that you're likely going to have steel sections that are not protected in grout.
Okay, a couple questions here about the testing for ultrasonic testing. So what kind of readout do you get from the ultrasonic testing? So what would be the report, the data you'd be capturing?
Okay, so you basically are going to get two waveform measurements from each measurement that you take. So if you remember back to the video that I showed, they were going along and taking a series of measurements going along the length of the tendon. So you're basically going to get wave profile measurements at each one of those measurement locations along the length of the tendon. And basically what you're going to see is when you've got a void, you're going to have a big difference or big deviation from the typical measurement that you're getting as you're going along that same tendon. So you're basically going to see that you've got something going on, and then you might have one or two more readings, and then it might get back to normal. So you can define that you've got something going on in that location, and you can probably get a reasonable idea of the affected length that you're dealing with there.
Okay. As it relates to the ultrasonic testing, the video you showed as the team went along the side of the girder there and testing for the voids. Do you need to do that along the top of the tendon or the side, or does it matter the orientation?
No, it doesn't matter. Well, you're going to do it from whatever side is available. There maybe theoretically there might be some advantages to do it one or the other, but the bottom line is that you're going to do it from whatever side is available. So in a beam or a girder situation, that's very often from the side, is the side that the face that is available to you. If you're doing longitudinal tendons in a bridge, you may also do them from the top at the high points, because you might have, for example, cast in place box girder bridges where the tendons come up into the deck and then go down, and the high points are where you've got a high risk of voids, so you may do those from the top, but you're going to do it from whatever face is accessible, that you have access close to the tendon, embedded tendons.
Okay, just regarding the magnetic detection testing technique that you presented, do metal ducts affect the testing in that method, or no?
Metal ducts can have some impact on the method, definitely, yes.
Okay, nice short answer. How often do you need to perform the drying process for these tendons? And my understanding would be that once you dry them out, you've more or less treated them. Yes or no?
In theory, if it's just a moisture problem and you dry it out, then everything's fine. Probably the bigger question to ask is whether or not they're likely to stay dry long term or not. So if you have a situation where the moisture is only there because maybe it got in during initial construction, then drying it out might be sufficient, and you just say that's good enough. If they're tendons, for example, inside a building where they're unlikely to be exposed to water or moisture in the future, then probably dry them and walk away. If they're in a bridge that's exposed to the environment, I think you need to really think about whether there's a chance that you get moisture back into those tendons at some point in the future. And if that is possible, or if there is a risk of that, then you probably want to do something beyond just drying. Drying may be part of the process temporarily, but you probably need to make sure you do something to make sure that either they don't get wet, so that might be some waterproofing or some other type of approach to make sure they don't get wet in the future, or you may do something like impregnation. Very often the drying and impregnation go hand in hand, or it could be drying and even filling of voids in the grout, or waterproofing the end anchorages, whatever. You're going to have, you don't have to do anything, but you might want to consider doing something to make sure that you get some long-term benefit from the drying if you're going to spend the time and the money to do that. Okay.
Any sense of the length of time it takes to dry? I know it's like, how long is a piece of string, right? How long does it take to dry a tendon? Well, let's just use a number and say 150 meter long tendon. How long would it take to dry a single tendon?
Right. So it's really going to depend on how good your airflow is in the tendon assembly. It's probably measured in months though to do drying. It's not going to be in minutes or hours like for doing moisture testing. It will be measured in certainly weeks or months, and obviously the more your airflow, the higher your airflow is, the faster that's going to go. The more permeable the grout is, the faster you'll actually remove moisture from it. So in a way, the worse your situation is, the faster it'll dry. But if you had really good, high quality, dense grout, and at the same time somehow had a moisture problem, you could have something that might take quite a long time to dry. That may not be a common thing that you would run into though, because if it's good quality, good grout, you hopefully don't have this other problem.
Gotcha. Okay, we have a question from a friend from Montreal, and I'll paraphrase. Is the impregnation method suitable for advanced levels of corrosion? So if you have concrete or grout distress and maybe even the duct cracking, would you get leaks when you're injecting or when you're impregnating? Would it be effective to do that?
Yeah, so you certainly you certainly could have leaks, and you could have leaks because if you had a metal duct, it's corroded. You can have leaks if you've got, cracks or defects in plastic ducts as well. So leaks is something you're going to have to deal with in the field as part of doing the work. And normally what we will do there is we will air test the ducts and try and catch as many of the leaks as possible before starting to do the work. It's always easier to seal them before you start pumping than after. But maybe the question relates to, if you already have some corrosion going on, can you do the technique? And the answer is yes, you can. As long as it's not corroded to the point that it's broken, you can at least slow down the corrosion rate, extend the life of the element. Obviously, it's not going to restore any steel that is corroded or any strands or wires that are already broken, but it will significantly slow down the rate of decay of what you have today. And so that's probably the way to look at it. It's a way to extend the service life, but it's not going to take you back to a brand new structure if you have a certain amount already corroded.
Okay, we're getting close to time here. We're a little over time, so just have a couple more here, all related to the impregnation method. What happens when you do impregnate the tendon? Does the material stay fluid or does it harden? What happens?
Okay, that's a very good question as well. The material is a very low viscosity liquid material. A portion of the material is absorbed into the grout itself. That tends to increase the viscosity, or it's less liquid, the material that's remaining, but it's still liquid. The material does harden if it's exposed to oxygen. So if there is oxygen available, it will harden, not into a brittle material, but into a more of a pliable film. So it will set up in the presence of oxygen, but if it's in a completely sealed environment, it will probably stay as liquid or liquidy anyway, for potentially forever, but a long period of time. The corrosion protection benefit doesn't seem to make any difference about whether or not it's in solid or liquid form, let's say.
Okay, last question here. Just, is there a suitable pressure? What's the average pressure needed to impregnate a tendon?
Okay, it's a good thing. The pressure is relatively limited. I would say I can't think of any cases where we would have gone over maybe 150 psi, or what would that be? That would be about 10 bar. In most cases, we're probably between 50 and 100 psi, or between 5 and let's say between 3 and 7 bar. And that's typically the kind of pressures that you will see used is in that range. The material is actually moving more as a result of capillary action than it is by the pure pressure that's being applied.
Fantastic. We'll close it off there. Thank you very much, Dave.
Okay.
I apologize to everyone who submitted a question that we couldn't get to today, but I encourage you to reach out to Dave directly here with the information on the screen. I'll leave it up for a couple seconds. I know Dave would be thrilled to hear from you, and Dave and I sometimes play a little game. If you can stump Dave, I think I owe you $20 because he's a very hard man to stump. So I'll leave that up here for a second. So looking to the future, we have 2 upcoming webinars, one on February 10th and one on March 10th. The first one is mitigating crevice corrosion and pack rust on steel structures with our good friend Peter McCloskey from the UK, and followed by evaluating as-built conditions with non-destructive testing with our man Bill Horn. Both exciting topics. We hope you'll join us for both. And this actually brings us to the conclusion of the presentation for today. I want to thank Dave Whitmore here for joining us and sharing your experience and your expertise with post-tension structures. I know it's valuable for all concerned. Dave, thank you very much.
Thank you, Scott, and thank you for everyone that attended the webinar. Look forward to hearing from you in the future.
Fantastic. Everyone else, thank you for lending your ears as always. We appreciate it. Now get out there and save some structures, and while you're doing it, please be safe. Thank you.